So after selecting a trial section, we have to check for a slenderness ratio. So we have to check for a slenderness ratio. That is the sixth step. So we have to select for a slenderness ratio. So before going into that check or that concept, so let me discuss the concept of truss. Clear? So let me discuss the concept of truss. Then only you understand about those provisions regarding slenderness ratio and that check. Clear? So now, before going into it, so tell me where you are going to find these tension members practically. Of course, so far we have discussed in detail about the design procedure of tension member. Agree or not? Yes, of course, we have discussed about the tension member. So now, practically, so whatever we are going to design here, obviously those things are there in the practicality, or in the field. So now, where we are going to see these tension members in field or in practically, or in practicality, sorry, in practicality or in field, where we are going to see these tension members? That is a question. So tell me where we are going to see this tension member. Of course, if we take beam in building, so the building where we are staying or where we are studying. So in all those cases, we can see the beam. Of course, we can see the column compression member. Okay, and we can see the foundation. But my question is where you are going to see the tension member. That is the point here. So where you are going to observe tension member. Of course, we can observe beam which is in which it undergo flexure or bending. Okay, and then column which undergo compression, so along with the bending, okay, in some cases, and footing, so it undergoes shear and bending. Now, where you are going to find tension member? That is the question. So the tension members we are going to find in trusses. Agree or not? So practically we can see the trusses. Agree or not? So in trusses we are going to see those tension members. Clear? So now, how many types of trusses are there? So in our design, so in this design or in our discussion, which type of trusses are more important? So that's the point here. So in trusses, we are going to find these tension members. So now, whatever the procedure we have discussed so far is applicable for the design of the tension members in the trusses. Agree? So in trusses, we are having the tension members. So now, so far, whatever we have discussed, that procedure is applicable or valid for the tension members in the trusses. So now let's come to the trusses. Where you are going to see the trusses more widely? Tell me where you are going to see the truss in practicality. Or practically where you are going to see the truss more widely. Come on, tell me where you are going to see. So mostly the major truss or most important truss in our design of steel structure is a bridge truss. So whenever you are going to see a railway bridges. So railway bridges, mostly the railway bridges are of truss bridges only. Mostly the railway bridges are of truss bridges only. Of course, nowadays we are shifting towards pre-stressed concrete bridges also, PSC gutters. So in place of truss gutters, we are opting PSC gutters. But if you see in olden days, wherever the railway bridge is there, in all those cases we have used truss bridge. Yes sir? Agree or not? So that is the location where we are going to use truss. And one more location, more widely where we are going to use truss is for supporting the roof. Okay, if we see the industrial building, if we see the industrial building, so there we are having those are called as industrial roofs. So to support those roof members, okay, roof coverings, we are going to use truss. That truss is known as roof truss. So mainly we are going to use more widely. So more widely or mainly we are going to use truss in two locations. That is for bridge as a bridge truss in railways, and then roof trusses in industrial buildings and some other locations. Clear? Mainly for industrial buildings we use, but not only for industrial buildings, for high-rise buildings also we are going to use the roof trusses to support that roof covering. Clear? So these are the two locations, but other than this we are going to use trusses some for other cases also. Like if you see in railway stations, to support the overhead tank. So that overhead tank is placed on the truss. The truss is vertical. Agree or not? Again, even in the same railway station, we are going to see the foot over bridges. We are going to see in the railway station foot over bridges, means to go from one platform to other platform, there exist foot over bridges. Yes or no? So if we observe that foot over bridge is placed on the truss. Agree? Again, that truss is also vertical truss. The truss in which the overhead tank is placed, okay, overhead water tank is placed, that is also placed on vertical truss, and the foot over bridge is also placed on vertical truss. So these are going to take relatively less loads in comparison with the bridge truss and roof truss. Agree or not? Do you agree or not? So in bridge truss, how much load it is going to take? So the moving train it has to take. So how much load that train will have? Moving train. So self weight of train itself is more, but along with that train, it is carrying goods or passengers, and then it is moving. Agree or not? So that is a very heavy load that bridge truss is going to take. Even if you take roof truss, of course the self weight of roof truss may be less, but it is subjected to the wind load. Okay, roof truss is subjected to the wind load. So these are classified as a horizontal trusses. So bridge truss is like this, yes or no? So train will move from here to here like this. So if you see like this, the train will move. So the truss is horizontal, and even the roof truss is also horizontal. But the trusses what I explained for, or what we have discussed for supporting the foot over bridge and overhead tank are vertical in nature, vertical in alignment, and they are going to take little less loads. So we are not going to discuss such type of trusses here. The reason they are going to take very less loads. Okay, that is not our concern here. Our concern is mainly bridge trusses and roof trusses. So we are going to discuss those. So here I am going to tell the slenderness ratios for those. Okay, so now I am going to take the bridge truss, and I am going to explain the members present in it. What are the effects the members present in that roof truss are subjected to? Okay, so I am going to take a bridge truss. What type of bridge truss? So once again I repeat, mainly truss, the trusses what we are going to discuss here is mainly bridge truss and roof truss. So remaining which are horizontal in nature or horizontally aligned. Clear? They are horizontally aligned, but we are not going to discuss about vertical trusses. Where we are going to use those vertical trusses for supporting foot-over bridges in railway station and for supporting overhead tank. We are going to use vertical trusses. So we are not going to discuss those vertical trusses here. So bridge truss. So I guess regarding this truss you have discussed in structure analysis, but still I am going to repeat that concept here and revise that concept. This is a simple truss. So now this bridge truss, okay, this bridge truss I am going to idealize as a simply supported beam with sagging case. So I am going to idealize this bridge truss as a simply supported beam with sagging case. Okay, simply supported beam with sagging case. SSB. Okay, simply supported beam with sagging. So what is meant by simply supported beam with sagging? So simply supported beam with sagging means above neutral axis, NA, neutral axis compression, below neutral axis tension. Agree or not? So now, as we discussed, so truss is nothing but simply support beam with sagging. The reason all top cut members, if you see a truss, so this one, so here I am going to name it U1, U2, U3, U4, U5, L1, L2, L3, L4, L5. So this U1, U2, one member, U2, U3, other member, U3, U4, another member, U4, U5, some other member. So in all these upper cord members, so these are called as upper cord members. So all these upper cord members are subjected to compression. Okay, all these upper cord members are subject to tension. You can take it for granted. Wherever the load may be, whether the load may be here or here or here or here. So that is subject to tension. And one more thing, the truss is subjected to axial forces only, be it a tension or compression, and that to the load act exactly at the joint only. So as I said, this is the concept of structure analysis. No worry. So I guess you have discussed or you are going to discuss in structure analysis. So load. So for trusses, load always acts at joint only. If at all load is not acting at the joint, then it is not called as a truss. So for the if you observe the condition for a truss, the condition for truss is the load should act at the joint. So because of that load is acting at a joint, the members of the truss are subjected to axial forces only, be it a tension or compression. Agree? So in that, all upper cord members are subjected to compression. Now all lower cord members are subjected to purely tension. Okay, our upper cord are compression, our lower cord are tension. So that is why I said simply support beam is sagging case. So above, if we take simply support beam is sagging, above neutral axis compression, below neutral axis tension. In the same way, all upper cut members compression, lower cut members all upper cut members compression, lower cut member tension. So now that is those are subjected to compression and tension irrespective of the location of the load. But between members, so there exists a between members like U1, L1, and then L1, U2, U2, L2, and then U3, L2, U3, L3. So these are the between members. Agree or not? So these between members are subjected to the reversal of stress. Okay, these between members are subjected to reversal of stress. What is meant by reversal of stress? Reversal of stress or reversal of load. It means, for example, assume that load is here. Load is at the joint L2. So because of the load is at L2, the force in the member U2 may be compression. Assume it. Okay, it is not you don't take it for granted. So it is not a real thing, but just an example I'm telling. So because of the load at L2, okay, load at L2, the force in this member is compression. The same load is at L4. Then, in the very same member, the force may be tension. That is what the reversal of stress means, or reversal of load means. So, because of the same load, but because of the change in location or change in position of the load, the force developed in that member may change. Okay, so irrespective of the location of the load or position of the load, all upper cut members are subjected to compression and lower cut members are subjected to tension. But with respect to the position of the load, the force in these between members will change. So that we can say in truss. Okay, in truss. So mainly bridge truss or roof truss, we can say all upper cut members are subjected to compression and lower cut members are subjected to tension and between members are subjected to reversal of stresses. And one more point here, if we take bridge truss, so in bridge truss, what is the major load? Okay, so bridge truss is subjected to which type of loads? Mainly, tell me which type of loads the bridge truss is subjected to. So bridge truss is subjected to live load, or you can also call as imposed load. So live load or imposed load means moving train mainly. Okay, that is a live load. And then its self-weight itself. If you see the bridge, so in that bridge truss, so it consists of structural steel members of channels or angles. So the self-weight of that steel is also way more, okay, very large. So then obviously the self-weight is also acting. So now bridge truss is subjected to mainly two types of loads. What are the two types of loads? Dead load and live load. Agree? Dead load and live load. So these are the loads the bridge truss is subjected to. Now if we take roof truss, so in roof truss is provided at some altitude, at some height it is provided. So at that height, obviously wind loads are predominant. So now based on this, roof truss is subjected to wind load also. So there, in comparison to the live load, wind load is predominant. So now roof truss is mainly subjected to dead load and wind load. Okay, dead load and wind load. That is the point here. And one more thing here. If we see the naturally occurring phenomena, okay, both wind load or both wind and earthquake load will not occur at the same time. Okay, they will not occur simultaneously. Yes or no? So, for example, there is a earthquake. Do you think or do you imagine a cyclone at the same time? No. For example, is there a cyclone? Or do you imagine earthquake? No, obviously. So, in the same way, the code has considered that if at all wind load is there, along with that, consider dead load, consider earthquake load also. It means both will not occur at the same time. So either consider wind load or earthquake load. That is the meaning of suggesting to consider those wind load and earthquake load combined. Okay. So it means if at all the structure is subjected to wind load, it means we are going to assume it is subjected to earthquake load also. But in real, it is not subjected to earthquake load strictly, but it is subjected to wind load only. But both the phenomena will not occur at the same time. So either consider wind load or earthquake load. That is the point. Okay, that is the point here. Clear? So once again I repeat. So for bridges, in bridges, which type of loads are more predominant? Dead and live load. In roof trusses, dead load and wind load. So we can say dead load, wind load or earthquake load. Okay, wind or earthquake load. Either this or that. So obviously that load that roof truss are subjected to wind load only. So this is the point. Okay, so this is where we are going to find tension members. So mainly we are going to find tension members in trusses. So the trusses we are going to use in bridges. Okay, as a bridge we are going to use a truss that is known as bridge girder or truss girder. Okay, bridges, the truss which is used in bridges is known as truss girder, and then the truss which is used in roofs are known as roof trusses. Agree? So for that we are having some slenderness ratio. Clear? So slenderness ratio is nothing but effective length by minimum radius of gyration. So check for slenderness ratio. So this is as per IS 800. So as per IS 800, some provisions are there regarding this slenderness ratio. It means after selecting a trial section from steel table, we have to check it. Why? Because we know the minimum radius of gyration for that selected section. Agree or not? And if you know the end condition, we can calculate the effective length. So that effective length by slenderness minimum radius of gyration, we are going to get slenderness ratio. Okay, so the check is there. So a member subjected to reversal of loads due to loads other than wind or earthquake. Okay, wind or earthquake load. Then maximum slenderness ratio. Should be less than or equal to 180. So a member subjected to reversal of load or stress, you can say reversal of load or force also we can write there. Okay, a member subjected to reversal of load or stress or force due to loads means applied loads other than wind or earthquake load, then maximum slenderness ratio is 180. So where we are going to find these type of members? In bridge truss between members. Okay, between members of a bridge truss we are going to find this. Agree or not? So if we take the between members of a bridge truss, so in bridge truss what is the major load? Dead and live load, but not wind or earthquake load. So other than wind or earthquake load. So this provision is for between members of a bridge truss. Agree? Next. A member is used as a tie. So tie is nothing but tension member. A member used as a tie in roof truss or bracing system. And subjected to reversal of load due to wind or earthquake load. Okay, so a member is used as a tie in. Tie means tension member. So tie in roof truss or bracing system and subjected to reversal of load due to wind or earthquake load. Now, which type of truss it is? In the name itself, roof truss. So in roof truss also we are having upper cord and lower cord between members. Agree or not? So now this provision is for between members and bottom cord members of a roof truss. For both the members, between and bottom cord members, this is the provision. But here this is only between members in a bridge truss. So now, in this case, L by R or KL by R minimum. So maximum slenderness ratio. So this is the maximum. Should be less than or equal to 350. So KL by R minimum is the slenderness ratio. This is R. KL by R minimum. So maximum. So maximum slenderness ratio should be less than or equal to 350. Okay, this provision is for the between members and bottom cord members of a or lower cord members of a roof truss. This is only the between members of a bridge truss. Okay, there exists one more provision. So first you take down. So later I will tell the next provision. First you take down to these two provisions. Now third. So next, for pure tension members. So for pure tension member, it means that member is subjected to only tension, no other force. Okay, no other force. So then KL by R minimum means slenderness ratio maximum should be less than or equal to 400. So these are the slenderness ratio for a tension member. Okay. So one thing I want to share here, this slenderness ratio check is more important for compression member in comparison with the tension member. Okay. So this is a check, merely a check, but this is not a most important criteria for in the design of tension members. Okay. In the design of tension members, the check for slenderness ratio is not an important criteria. Just merely a check we have to carry out it. But for compression member, it is going to influence or it is going to govern the total design. So, okay, slenderness ratio check is more important or governing criteria in design of compression member in a comparison with the tension member. So here, simply remember the provisions given are mentioned in the code. Okay. So this is the design procedure. So this is the design procedure for a tension member. So the simple thing. So once I repeat the design procedure. So what is the first step? Decide the load and multiply with load factor. So first decide the factor design load. After that, decide the permissible stress as per IS 800/2007. After that, calculate the area. So here we have to calculate net area. So after calculating the net area, we should calculate gross area. The reason in steel tables it is mentioned the gross area but not net area. So for that, calculate the gross area. How to calculate gross area? Either increase that net area by 25 to 40% or based on gross section yielding, we are going to calculate gross area. So after getting the gross area, that is nothing but area required. So now we came to know this much of area is required to take that factored tension load. Okay, factored design tension load T. So after that, what to do? By taking a steel table, we have to select a trial section. So be it angular, channel or I section, whatever it may be. But mostly we prefer angular channel as a tension member. Of course, we can use flats and bars and so many other members also. But in bridge truss, mainly I am talking about bridge truss. Why? Because it is only the truss which is subjected to major load. So that is our prime concern. So if you see any bridge truss, okay, truss girder or steel bridge truss. So in that we are going to use channels or angles as members in the truss. Agree? So in that, select in the steel from the steel table, select either angles or channels. Means simply select a trial section so that the trial section will have some area, gross area, which is mentioned in the steel table. So that gross area which we are going to provide should be greater than or equal to gross area how much we have required. Okay, or how much we have calculated. That is the design procedure. So after that we have to check for slenderness ratio. So there is some provisions given by the IS code book. Okay, there are some provisions in IS 800 code book. So according to that, so whatever the section we have selected, so that section should have or should meet those slenderness ratio criteria, or else we have to redesign it. Agree? So this is the design procedure of a tension member. Clear? So very simple. So next topic, lug angle. So the next topic here is lug angle.